welcome to this little video about the propagation saw test. My name is Dave Coche. I'm with Queen's University in the Department of Geological Sciences and Geological Engineering. I worked on this project while I was at the University of Calgary. I worked with Bruce Jamieson and Cameron Ross. Today I'm going to go work through some of the methods that we developed for the propagation saw test, or PST, the way to interpret the results, the way to record the test results, and some of the research we did to validate the test. So the first thing that we need to do before we talk about the test is answer this question: why do we even need one? And I think this photo here says a lot about that. There's a group of skiers here in this orange circle along the ridge line, traversed along. They started a fracture in the weak layer at the ridge line, and that fracture propagated down the slope and around and back up on the looker's right side here and released a really big avalanche. And the size of that avalanche doesn't really relate well to the amount of energy that those skiers were putting into the snowpack. So right there we have to separate the initiation of the fracture from the propagation of the fracture across the slope. We have a lot of tests already, or we had a lot of tests already that were good for the initiation part, compression tests and root block tests and things like that. And we didn't really have anything that was saying something specifically about the propagation part. So a test that could answer this question that the guide or the forecaster might have here: what's going to happen if we start a fracture in the weak layer? Is it going to propagate far and wide and release a big avalanche, or maybe not propagate at all? So we set out to try to design a test that could answer that question. So let's get right to it here and see the test in action. A little video is going to come on in a second here showing Catherine Brown actually doing a propagation saw test. In this case, the weak layer is down something like 40 centimeters. It's a surface hoar layer, and this little block of snow that Catherine is cutting into, she's dragging a snow saw along the weak layer in a column that's completely isolated from the surrounding snowpack. It's about 30 centimeters wide in the cross slope direction, so that's the way that her saw is pointing, and about a meter long parallel to the slope. So this video is taken sort of from someone standing up above the pit. And you watch, she'll just drag the saw through the weak layer. That's the blunt end of the saw, makes it really quite easy to stay in the layer. And she's going to watch for the point that the fracture starts running ahead or jumping ahead of the saw in the weak layer. And she's going to mark that spot with her saw and then watch what happens.
Ready?
Yep.
So we just saw a pretty good example of the propagation saw test in action. You isolate this block about 30 centimeters wide in the cross slope direction, about a meter long in the slope parallel direction, and that's for shallower slabs. We tend to highlight the weak layer with a paintbrush or the back of the glove just to make it easier to drag the saw through. And then you put the saw in at the downslope end and start dragging it up the slope. Now you see there's a little star beside the 1 meter column length here, and that's to say that the 1 meter length is great for slabs that are up to 1 meter thick. When you get into deep slabs, which this test works perfectly well in, you want to make sure that the test is at least as long as the slab is thick. So if it's a 2 meter thick slab, you want to use a test column that's at least 2 meters long. So I just put this little picture in here just to show that you can do this test on steep slopes, on shallow slopes, in start zones, on safe slopes, and on flat terrain, even in quite deep slabs. In this case, the slab is about almost 2 meters thick, and we're just about on perfectly horizontal terrain. And I cut from the one side of the column, the short side there, to where the saw is, and the fracture propagated right across the column for the remainder of the way. And it's brown there, just so we put some hot chocolate powder on it to be able to see it better. A bit of research has gone on into how the slope angle affects the results, and basically if there is an effect, it's quite small, and definitely small enough that the tests are valid done on flat terrain. So we'll just show one more video here. This one is of Thomas Exner in a test column that's extra long. So this one's almost 3 meters long in a slab that's about a meter thick, another surface hoar layer. And I put this on here to highlight the results that you're looking for that are going to suggest high propagation propensity, or that there is a propensity there for fractures to propagate once they start. So in this case, Thomas is going to cut about 30 or 40 centimeters into this thing, maybe a little more, and the fracture is going to go shooting up the slope, and it's going to make it all the way across that 3-meter long test column. And we did some research that showed that if you can cross a 1-meter column, it'll cross a 2-meter column and a 3-meter column, and so on, up to the probably up to the size of the slope, and that's where we're getting that sort of connection between the test and the process that's going on the slope scale. So what you want to look for is the amount of the column that you have to cut to get the fracture to start, and then watch how far the fracture goes. Does it go all the way to the end? Does it stop somewhere within the column? And does the slab break? Sometimes there's a fracture through the thickness of the slab. If that happens, it tends to arrest the propagation, and that says something. So in that video, you could see that Thomas was quite pleased with himself and with the propagation that he was able to get in that test column. Like I said, that one was about 3 meters long, but the cut length was about the same, even in the 1-meter test we did just before that. And it's just to show that when you get really good propagation in the test column, you don't have to cut much, and it propagates all the way to the end. So that's the condition, that's the result of the test that says that propagation is likely. If we trigger a fracture in that weak layer, it's probably going to propagate, or it seems like there is high propagation propensity in that snowpack. So here at the top I've got this propagation likely condition. So if you've got, say, a 1-meter column or a 2-meter column, if you've got a deep slab, if you have to cut less than half the column to get propagation to start, and it propagates right to the end without interruption, that's the test result that's saying there's high propagation propensity in the snowpack. And that makes sense. It's easy to start, and once it starts, it goes great, just like on the slope scale during avalanche release. Now, any other result means that propagation is not likely. The test is suggesting that this snowpack doesn't have high propagation propensity. So if you have to still have to cut less than half the test column to get propagation started, but the propagation arrests at a slab fracture, or it just stops somewhere in the column, it doesn't make it all the way across. That's suggesting that there's low or no propagation propensity there. One other condition is if you have to cut more than half of the test column, so if you have to cut 3/4 of the way or something close to the top end to get propagation to start. If it goes to the end, or if it goes all the way to a slab fracture or whatever, it doesn't matter. If you have to cut more than half the column, that's suggesting that propagation is not likely as well. So we created a little recording standard that we worked out after having done the research for a couple of years, and we've put this out. If you look on the website ucalgary.ca/asarc and search the publications, you'll find a PST how-to on there, and we have the recording standard indicated. Anyways, what we suggest is in the second row here, PST X over Y with the arrest condition in brackets, and then similar to other tests, down Z on a weak layer date. So in this case, X is the cut length and Y is the column length. So if it was 20 centimeter cut on a 100 centimeter column, it would be PST 20 over 100. If it propagated to the end, which would indicate high propagation propensity, you would just put end in the brackets. If it went to a slab fracture, you might put SF if it just arrested ARR. So I think that's fairly straightforward. And then down Z is the depth to the weak layer, so that gives you slab thickness, and then the weak layer date, just so we can connect test results from place to place. There is a standard in the American Avalanche Association SWAG document. There's a draft standard for the CAA's ogres, and there's other international versions of this for the PST. So if you, it's probably worth checking on your local standards. So the next big question, of course, is does the PST work, and why do we think that those certain results indicate high propagation propensity? Well, so what we did was we skied around on our way to make ski cuts. If we triggered a whumpf, or triggered an avalanche accidentally, or triggered an avalanche with a ski cut, we knew that we had triggered the fracture, so we had initiated a fracture, and we also had observed a fracture propagating. What we also did was we stomped around and did a lot of ski cuts, and when we didn't get an avalanche or a whumpf, we excavated our tracks and made sure that we had indeed fractured the weak layer, or we had initiated the fracture, and it hadn't propagated. So that's a really kind of tricky way, but it gets us at being able to differentiate between cases where we initiated and it didn't propagate, and cases where we initiated and it did propagate. And that's the difference that this test is supposed to be sensitive to. So we did this at 120 different sites over 4 winters of validation testing, and that includes 247 individual tests for this validation data set. So if we go back to the table here, I've just filled it in with some of the numbers. So there was 117 tests that predicted propagation right next to whumpfs and avalanches, and there was 5 cases where the propagation saw test predicted propagation, but it wasn't observed. So we initiated a fracture, but it didn't happen. 55 cases where the propagation saw test said no propagation, and we were right beside a whumpf or avalanche, so we knew that it was possible. And another 70 or so cases where the propagation saw test predicted propagation, did not predict propagation, or predicted no propagation, and we also observed no propagation. So we had initiated fractures below our skis, but no avalanche or whumpf had released. But the correct predictions are the ones that are yes for predicted, and yes for observed, and no for predicted, and no for observed. Those are marked in green there. So the propagation saw test was correct in 76% of the tests in this validation data set. It was wrong the rest of the time, so it's at 24% or so. Now, the false unstable rate, so times when it said, you know what, there's high propagation propensity here, but we didn't observe it, was really low, 2%. That's quite good. The real problem here is what's marked in red, and that's the false stable rate. So those are the dangerous ones, when a test says there's no propagation propensity, or you're in a stable snowpack, but it's not. Places where the test said no propagation propensity, and we were standing right beside a whumpf for avalanche. So that's 22% of the time. That's higher than most other instability tests that we have, like the compression test and the Roosh block test, in particular the extended column test. But in the case of the PST, we do quite well with the false unstable. So you're giving up a bit of one mistake for the other. So this is not a replacement for the compression test or the Roosh block test or even the ECT, which is probably telling us something good about both the initiation and the propagation. This is a test to use when you have a specific question about the propagation propensity of a snowpack, and you can use it on steep slopes, shallow slopes, in thin slabs and thick slabs, anywhere that you care to dig. And there's a lot more information about the propagation saw test, that work that was done at the University of Calgary by, again, myself, Dave Gauthier, and Cameron Ross, and Bruce Jameson. So if you just head to this website, ucalgary.ca/asarc, there's a spot there where you can go to publications, and just search the publications for PST or the word propagation, and you should get everything there. There's a couple of theses on there, a couple papers, and some of this little how-to reference card that you can take in the field. Thanks very much for watching.